Ladies and gentlemen, the subject of my talk is optimum energy harvesting among distributed power sources with maximum fault tolerance. Let's start with motivation for energy harvesting among distributed power sources. Existing architectures of satellite power systems already adopt distributed solar resources. Each solar resource is interfaced by a DC-DC converter, forming a controlled power channel. Outputs of distributed power channels are parallel connected to form a system output voltage. The system output voltage is regulated by these distributed input parallel output converters. I call it dipole converters. Maximum power tracking, or MPT, for distributed power sources should be made simpler without use of many MPT controllers that dedicate for each power source, since their peak power voltages are similar. There exist three approaches of energy harvesting. The first approach is drawing equal current from each source using uniform current distribution, or UCD. The uniform current distribution of all distributed sourcing currents, I call it group tracking UCD or GT-UCD. The second approach is keeping equal voltage across each source using uniform voltage distribution or UVD. This particular control also do it for all distributed sourcing voltages. I call it group tracking UVD or GT-UVD. And finally, the third approach is independently tracking peak power voltage of each source using independent maximum power tracking. I call it IMPT. This particular control approach dedicated to each power source. Okay, let's review the approach number one, which is called group tracking uniform current distribution. This approach is the worst approach. Despite the possibly equal peak power voltage of the distributed power source that pre-selected, their sourcing voltages are not equal since they are not controlled, and the achieved peak power is often too far below the ideal peak power. Practically, power sources with the same or similar peak power currents are very rare and not consistently obtainable. Now let's review the base approach, which is independent maximum power tracking or IMPT. This particular approach have independent maximum power tracking controller dedicated for each power source, and each controller produce the maximum power voltage candidate VMP1, VMP2 and VMP3 that serve as a controlling signal to controlling the peak power voltage across each power source. E1, E2 and E3 are control voltage signals, where IS1, IS2, IS3 and RS1, RS2, RS3 are the parameters of three power source number 1, number 2 and power source number 3. The advantage of the ideal of this approach is that the ideal peak power is achievable since peak power voltages of individual power sources are independently tracked. The disadvantage of this approach, IMPT, is the most control complexity and computation, leading to much more component counts. Okay, let us focus on the main core presentation that I'm going to apply and describe it in detail. The approach number 2 is group tracking uniform voltage distribution. In this approach, E1, E2 and E3 are controlled voltage signals that represented by controllable converter. IS1, IS2, IS3 and RS1, RS2, RS3 represents parameters for each power source PS1, PS2, PS3 respectively. This approach uses only one MPT controller. Tracks the whole system peak power voltage. Even though we may have different peak powers existing among power sources. Power source number 1 and number 2 and number 3 may have different peak powers. Sourcing voltage across these power source VS1, VSA1, VSA2 and VSA3 are controlled to be equal. Let's review the feasibility of the group tracking uniform voltage distribution harvesting approach. The group track UVD provides a nearly ideal transfer of the maximum power, less control complexity, multiple power fault tolerance, up to n-1 faults for the system of n distributed power sources. Distributed power sources and distributed input, parallel output or dipole converters are controlled for equal input voltages across their respective sources and tracking the system optimum power point that is sufficiently close to the ideal system peak power. Let's understand the definition of group uniform voltage distribution, particularly optimum power transfer. The system optimum power is, by definition, the maximum power drawn from the distributed power sources while keeping their equal voltages. With proper input voltage distribution control, an optimum utilization of power sources is achieved by using only one MPT controller and eliminating distributed independent maximum power tracking controllers, each of which is conventionally dedicated to its respective power source. This chart shows the DC characteristic between power and voltage from 3 different approaches. The x-axis represents the system sourcing voltage, which is the summation of all distributed voltages together. The vertical axis is the summation of all the power delivered by the distributed power source. The base approach, which is IMPT, provides 842 watts. which is nearly 100% tracking efficiency out of the ideal peak power, shown in the top curve with the highest peak. The worst approach is labeled with the GTUCD, which is Uniform Current Distribution. Deliver only 88% tracking efficiency, which is about 751 watts. The optimized approach, which is the main core of this presentation, is group tracking uniform voltage distribution. This delivers 98.7% tracking efficiency, which is already very acceptable.